We've already talked about probability distributions. And in fact, we've already created this exact probability distribution, which I copied and pasted from a hands-on code demo that we did earlier. But now we can define a probability distribution more formally. So specifically, this distribution describes the likelihood of a random variable. Now we know what random variables are. That was the topic of the preceding video. So a probability distribution describes the likelihood of a random variable taking on its possible values. So in the case of an experiment where we have 5 coin tosses, there are 1, 2, 3, 4, 5, 6 possible outcomes in that case, and this probability distribution describes the likelihood of those particular outcomes. So the probability of throwing 2 or 3 heads in 5 tosses is much higher than the probability of tossing 0 or 5 heads. This distribution here is an example of a probability mass function, or PMF. So I've just copied it again here. A PMF is a function that describes the probability distribution of a discrete random variable, as opposed to a continuous one. So, there's no such thing as 1.7 heads out of 5 coin tosses. This is a discrete random variable, not a continuous one. The notation for a PMF is a capitalized, italicized letter P, and we distinguish different PMFs by the random variable that they describe. So if the random variable x is being described by the PMF, then we have this unitalicized variable x, or if we're describing this other variable y, again, we have the unitalicized random variable y when we're speaking about them in the abstract without any particular values. To note, that same variable x is italicized, just as we discussed in the random variable video that preceded this one. It's italicized here because now it represents some specific values, whereas here it doesn't. It's just in the abstract. To dig into that idea a little bit more, the probability of a particular state x, say getting 2 heads on a 5 coin toss, that specific probability with italicized x means that we're now talking about the probability of a very specific outcome. So here we're just talking about the probabilities associated with some random variable x. Here we're talking about the probability of a particular state. So we could say the probability of a 0 is 3.1%, for example. And so any of these notations here mean the same thing. So if you see those, they always mean the probability of a specific outcome. In this notation, or this notation here, we're saying the probability of some random variable x being some particular state of x. And same thing here. It's the probability of some random variable x being some particular value of x. So, for example, I talked about this without having the example here in front of us already. So the probability of some variable x being some particular state x. So for example, the probability of the random variable x being equal to 2 is, in this case here, 0.31. There are 3 essential properties of some probability mass function for some variable, say x. So the first is that it covers every possible value of x within the domain. So, for example, with this one here, where we have 5 coin tosses, there are 6 possible outcomes. We could have 0 heads, 1 head, 2 heads, and so on. And so every possible value of x must be included. The second essential property is that every individual Px, so italicized x, so every particular state, the probability of any given particular state, can only range from a probability of 0 to a probability of 1. It can't be outside that range. And the sum of all of the individual probability states must come out to a total of 1. So in this example here, if you add up the height of each of these 6 columns, you'll end up with a total height equal to 1. That final property, by the way, is called normalization. Okay, so that covers probability distributions for discrete random variables. Up next, we'll talk about the distributions for continuous random variables.